Hello, my name is Philip Meriton, and today we are going to have a conversation beyond science and religion. Now, my website is heavenattheendofscience.com, where you can learn about my book of the same name and my own views about the debate between science and religion. Now, the purpose of this show is to break through the common beliefs and perceptions that tell us how to think about the world and ourselves. Unless we question these beliefs, we will never know if they are correct. Now, the most common beliefs we hold are rooted in the scientific worldview. This is a way of thinking that is sort of like the operating systems to our mindsets. We have handed scientists a job of giving us a system to understand the world. In response to that, they have drawn models of reality. The model that currently guides the way we view the world goes by many names, but one of them is called the quantum field theory. In each instance, scientists develop a model, and then, as the thinking goes, they compare the model to reality. Now, none other than Albert Einstein gave a standard to judge the completeness of a physical theory. He said, "Whatever the meaning assigned to the term complete, the following requirements of a complete theory seems to be necessary. Every element of the physical reality must have a counterpart in the physical theory." So the idea here is to conform a model, a theory, with the physical world, to have them correlate, to have them align with each other. For those who want a more common example, the one that comes to my mind is when a basketball coach calls timeout and draws up a play on a piece of paper for his players. He's drawing up a model of how he wants the players to move on court to score a basket or to defend the goal. Now, science is the same way, except science, we are trying to draw a model that aligns with the physical world that is supposed to be independent of theory. According to the scientific method, if the model or hypothesis does not fit the data, it means there's something wrong with the theory, not something wrong with the data. For as John Adams, our second president, said in a different context, facts are stubborn things. Now, if you decide that instead of adopting a different model, to change the data or the facts to fit the model, we have a word for that. The word is fudging, or adding a fudge factor. Now, the term fudge has an uncertain origin in this context. It seems the term can be traced back to the 17th century, and in its earliest sense it meant to contrive clumsily. An example of an etymology that perhaps says it all. This is also a really good word to look up in a dictionary, by the way, because there's all sorts of helpful definitions. Another one is to act dishonestly, to cheat. Wikipedia defines fudge factor as a quantity introduced into a calculation to fudge the results, to make them match better what happens in the real world. We have a good example of fudging with the current crisis in global warming, where it looks like some climatologists who very much want global warming to be true, in fact, fudge the data to show a warming trend not reflected in the real world. So maybe there's global warming, maybe there's not. But when you fudge the data, when you alter the data to advance a preconceived notion rather than just look at the data, your thesis loses credibility. Now, this show is about fudging on an entirely different scale. It's not the sort of fudging we'll read about in Newsweek, the New York Times, or Scientific American, and it's not yet made the show 60 Minutes. But it may very well be the biggest and most outrageous fudging of them all. Our scientists, even those who have won the Nobel Prize in Physics, may be fudging the very theories of reality. Now, this is important because this theory, the quantum field theory, the standard model of particle physics, are taught in school, they're written in textbooks, and they're guiding the popular scientists' books out there on the shelves, including, for example, A Universe from Nothing by Lawrence Krauss talks about it, and Lisa Randall in her book Unraveling the Mysteries of the Universe's Hidden Dimensions also talks about fudging. But to challenge this fudging, to open up the problem, to expose it, is heretical in today's mainstream science. It's blasphemy. But let's ignore this problem for a moment, and let's just be scientific about it. Let's look at the facts. Now, today our guest is Dr. Christopher Oakley, who is kind enough to join us today from the United Kingdom. Dr. Oakley has a degree from the Department of Theoretical Physics at Oxford University, and then after spending some time in the academic community, he now works on programming for a number of financial institutions. Well, thank you very much, Dr. Oakley, for joining us. Welcome to the show.
Thank you very much. It's nice to talk to you.
Okay, now the reason why I wanted to have you on the show, Dr. Oakley, is that you've stuck your neck out and challenged the scientific use of this fudge factor. I think it goes by a bigger name. I think the name is called renormalization. Is that right?
Yeah, and renormalization. I mean, shall I explain the etymology a little more?
Yeah. Why don't we set the table for the listener for a moment? Why don't you go ahead and explain this?
Yeah. Well, basically, quantum mechanics was a victim of its own success. It was devised originally around 1925, and within about 5 years, they were actually struggling to find new things to explain with quantum mechanics because it just seemed to be so good. Initially, it was to explain atomic spectra, but they were soon extending it to, just in very simple atoms like the hydrogen atom, but soon they were finding it was applying to pretty much everything they looked at. But one area where it fell down in was when particles are created and destroyed. Now, this happens quite a lot. Whenever you switch on a bulb, for example, what happens is the atoms move from excited to de-excited states, and in the process, they create a new particle, which is called a photon, and the photon is what comprises light. And the theory that they came up with, the quantum mechanical theory, was called quantum electrodynamics. The problem is it only works if you don't ask too many questions. And one of the original founders, Paul Dirac, who's probably one of the most unsung heroes of physics. He's a very well-known physicist, but hardly known at all outside the physics world. And yet he was pretty much of the caliber of Einstein. He never accepted it. And Richard Feynman, who more people have heard of, never accepted it really either. But apart from those two, it's pretty much heretical to say that quantum electrodynamics doesn't work. And at the core of this non-functionality is this process called renormalization.
Yeah. Okay. So we read a lot about how quantum electrodynamics is the most accurate theory ever devised, about how its predictions are good to several decimal places past a part in a billion, and it guides the working of technology, and it's the greatest thing since sliced bread. What is the underlying problem here?
The thing is, there's no sort of definite level at which a theory has to apply. So I could, if I'm allowed to come up with not very elaborate theories, I can explain an awful lot. If I want to come up with a very deep theory, then it's harder and there's more chance of it being proved wrong. Now, it's the way, if you're allowed to cheat in getting your 11 significant figures of precision in quantum electrodynamics, then of course you can get it. I mean, I can just say my theory is that the muon's anomalous magnetic moment is, and then write down the number, and I know that number from experiment, and then I can say my theory then works. The muon's magnetic moment is indeed that number. But what does that prove? The answer is not very much. I mean, they have the theory of quantum electrodynamics that is in operation now and has been for well over 50 years, is essentially one where they have allowed themselves to violate basic rules of mathematics. So even if they've got this precision, it only raises more questions as to why, because there's no underlying explanation that goes back to the principles of quantum mechanics.
Okay, so we've used some pretty strong words here. In my introduction, I did use the word cheat, and I did use the word fudge factor. Now, and you just used the word cheat. Let's try to describe why this is cheating. What is wrong with renormalization? What is the trick, the mathematical trick here?
Well, they come in various shapes and sizes. I mean, you mentioned someone fudging experiments in order to demonstrate global warming. Um, Before I go any further, I would like to point out that I'm agnostic on this. I don't have strong views pro or against. Um,
Right.
but on the other hand, the process of fudging experiments, I do have very strong views on. And it doesn't actually prove anything. If you're allowed to change the results to suit, so-called experimental results, then you have proved absolutely nothing. The difference between the fudging an experiment, whether it's climate change or whatever, um, and what happens in renormalization is that in quantum field theory, the results aren't wrong; they're infinite, so they're worse than wrong. What happens is the mathematics just simply does not work. You get, when you do a calculation for a very simple process, for example, the radiation of a photon from an excited atom, which happens billions of times every time you have a light bulb on for a second. Um, then um, uh, uh, if you get an infinite result, it's not merely wrong, it's just meaningless. The mathematics doesn't make any sense. And what renormalization amounts to is putting in artificial limits on the calculations that prevent the results from becoming infinite. But the remedy for this is not that, it's just to pair everything up and start again. You cannot fudge an infinite answer to a finite one. It's even worse than fudging a finite one to a different finite one.
Yeah, now I'm not a mathematician, so I'm going to try to describe the way I understand this in very simple terms. And the way I understand this is that if you are consistent in applying the principles of quantum theory
Yes.
to particles and forces, then
Uh,
you come up with an infinite answer. And that would be, some people say it's the virtual particles, and I guess it's the vacuum energy and et cetera, et cetera. But just to be very simple, if you're consistent, you get infinite answers. And obviously, if you're working on a problem and your answer comes out to have an infinite uh, value in it, something must be wrong, right?
Well,
Some
it depends on what you're trying to measure. I mean, there are some things that could quite legitimately be infinite. I mean, for example, we believe that the photon has mass zero. So if the quantity you were calculating was a reciprocal of that mass, then it would be infinite. But the point is that the infinite quantities they're calculating are things that are perfectly measurable and perfectly finite that you can calculate in a laboratory. So they obviously should not be infinite.
I see, I see. So what is the problem here? Then they have this quantum field theory, which is the mathematical structure or the mathematical rules for the model, but the actual data there that they measure is not infinite. Is that
No, that's right.
is that
Well,
right? Okay,
of course not. Yes,
okay,
because I
okay.
mean, otherwise you wouldn't be able to measure it.
Right.
Something like, for example, the scattering cross section in Compton scattering is a very well-defined thing that can be set up in a laboratory, and it obviously won't be infinite because you wouldn't be able to do the experiment if it was. Um, just to explain a little, quantum mechanics concerns systems where there are no particles created and destroyed. And as I explained earlier, it's probably one of the most successful scientific theories of all time, and certainly one that has impacted um, humanity possibly more than anything else, because we wouldn't have semiconductors if people hadn't understood quantum theory. Without semiconductors, we wouldn't have modern computers, modern communication, etc.
Right.
Now, quantum field theory is the extension of quantum mechanics to allow for the creation and destruction of particles. Most notably photons, because photons were the first particle that people ever were interested in over and above the particles comprising matter. And because, of course, light is everywhere, and light is something that is of huge interest to us. But the problem was that once you extended quantum mechanics in what seemed like the obvious way, in order to allow for creation and destruction of particles, then suddenly all these infinities started to appear.
Okay, so here come the infinities, and so the choice seems to be either come up with a different theory or different mathematics where there are no infinities, or to dust the infinities under the rug.
Well, yes, and I can tell you without any danger of contradiction from any people currently working in the business, that the choice has been made for the latter.
Right. It's a sweep. Okay, now how is that done? How have these infinities been swept under the rug?
Well, I mean, there's all sorts of ways of doing it. I mean, they have dimensional regularization, where what you do is assume that the number of space-time dimensions is something other than three space and one time. So, in other words, four, which is the standard. And then you calculate in this weird number of dimensions, and then you have a process called a limit, where you pretend that you can extend that back to 3+1 dimensions. Another one's the much more simple one is you take integrals, which is a mathematical construct associated with calculus, and which appears a lot in quantum theory. And then you arrange the integral. You basically cut it off. So you say an integral that would go up to infinity doesn't. It goes up to a cutoff level, and then the cutoff then becomes a parameter. It's not something that makes any kind of mathematical sense, but people seem to be quite comfortable doing it.
The again, to put this in simple terms, the way I view this is you have an infinity, a value of infinity on one side of an equation, and on the other side of the equation you add a negative infinity.
Well, that's how they. Yes, that's right. That is how it.
Is
That's
it
what
that
it
simple?
amounts to.
I mean, and there's this term called renormalizable, which
Yes.
if you read some of these popular science books, and the reason why this is an important topic, folks, is because this is a subject in many of the best-selling popular science books, such as The Grand Design, as I mentioned. It's in Lawrence Krauss's new book, um, a Universe from Nothing. If you look for the word infinities or renormalizable or fudge, you'll find a discussion on this. But what's amazing to me is this concept of renormalizable, where it looks as if, to me, the physicists have gotten lazy, where they've said, well, if there's a theory that even though there's errors in it, even though there's infinities, if it's renormalizable, or put in different words, if it's fudgeable, then it's okay with us. Because and is that something that you've noticed, this concept of renormalizable?
Oh, yes, of course. Yeah. I mean, essentially, quantum field theories are classified into renormalizable and non-renormalizable. I make no distinction, but I'm in a minority of one in this. Everyone, as far as I'm concerned, they're both broken, and both categories are broken. But that's the reason why we don't have a quantum theory of gravity, is because they can't figure out a renormalizable way of doing it. But no, I mean, essentially they have a rule book for doing renormalization, and no doubt there is something in it. It's just my argument is that they're claiming to drive a Cadillac when in fact they're driving a beat-up old Fiat Panda. Essentially the quality of the product is much lower than they're leading you to believe. There is a rule book, and they are following their own rules, but the rules are not very deep. And it seems that if you point this out at some point, then people just try to pretend you don't exist.
It's amazing to me, and this is going to be sort of a strong statement, but it's amazing to me that some of our leading scientists actually believe that they're going to come up with a theory of everything that includes a fudgeable or renormalizable term. It can't be right. How can they expect there to be a theory of everything as Einstein and others envisioned that has a factor that they're making up?
Well,
This
we
this
actually have double standards here. Whenever I confront any one of my former colleagues or other people in particle physics directly on the issue, at least on the record, um, they more or less agree with me. Sorry, off the record. If it's off the record, they more or less agree with me, and that this is something they would rather not have to do. This whole renormalization thing. And one of the things that was selling supergravity, this is 30 years ago when I was working on related areas, was the fact that it was finite. I mean, what they call finite is what I call consistent. In other words, you don't have to do renormalization.
right.
And if they're going to say this thing is so wonderful, it's finite, gasp, they're amazed and they're happy about this, and that's why they should work on it, then they should not at the same time be saying that renormalization is okay, because if they are impressed by something that doesn't have to use renormalization, they should be consistent.
Right. Yeah, and I think that we're entering now into this area of sociology, and you talk about this in your on your website, and you cite a couple. I think one book in particular, which is the book on string theory, called "Not Even Wrong" by Peter Voigt. And there's
Peter Ward,
another
yes,
right. There's
yes,
another one that's similar by Lee Smolin, "The Trouble with Physics." That's all about
yes,
and they're both about string theory and about how unless you join the band and go along with the mainstream scientists, physicists who are studying string theory, then you're not going to get admitted, you're not going to get the grant, you're not going to get the jobs, the PhDs. And this, to me, is very similar, but it could even be worse. Um, it, do you agree with that? I mean, you've essentially been ostracized because you don't go along with renormalization. Is that right?
well, no, that is true, yes. I mean, certainly, um, I would put it slightly differently. I would say that the onus was very much on me to choose a fashionable topic in 1984 when I was applying for postdoctoral jobs. And looking at ways of avoiding renormalization was not a fashionable topic. So that's why I didn't get anywhere with my job applications.
Right.
So in other words, that it's straight is the path that leads to salvation. You have to choose very specific areas, lines of inquiry, so that somebody will take you on. And because what was then the older generation for me, had failed to solve this problem, the assumption was that I couldn't, and there was no point in me even trying. But since I found out that a lot of the ideas I had looked at as ways around renormalization were far from being new. It's just that people had not followed them up. Interestingly.
Well, what do you think this says about the state of science today? The fact that new ideas, or even radical ideas that challenge the orthodox viewpoint, are shutted to the side and ignored. Where to me, I thought science was supposed to be the open-minded, objective inquiry into the truth. What do you think about what this says about the state of science?
Well, I mean, science is made up of human beings. Human beings are motivated by things other than the pure quest for truth most of the time. Um, the unique thing about particle physicists is that they would, and I think it's changing now because the subject is slightly being eclipsed by molecular biology and other areas where the brightest people go. But it's certainly when I was applying, um, the brightest people in the sense of the top mathematicians and physicists would be going into particle physics. And, you know, I can't in all honesty, say that I was one of them because I got good marks, but I wasn't top of my class. But on the other hand, I was good enough to get a research post. So it gave me a chance. But you see, the point is there's no one, if someone is at the top, there's no one to tell them they're wrong. And that was the issue, the problem with the likes of Feynman. He was so brilliant that even when he was making a mistake, there was no one who felt qualified to tell him that he was wrong. And I think this same generally, I mean, in fact, Feynman was better than average at sort of knowing when to apply a correction to the killer. But the problem is if the best and brightest mathematicians and physicists in the world are doing something stupid, who's going to tell them that they're doing something stupid?
Yeah, it reminds me of the importance of thought leaders, and that's the I think the term that best describes the situation. As you say, if the thought leaders, the people writing the textbooks, getting the Nobel Prizes, are going along with this approach, it's awfully hard to change the direction. Now, it seems like every other show I mention the same quote from Max Planck, who said that science progresses funeral by funeral, which I think is sort of a not exactly the most optimistic way to view things. But it's amazing to me that we don't have more people raising their hands, more leaders raising their hands and saying this has got to stop. And I think the analogy to global warming, although it's not a precise analogy, but if you look at what impact the climate gate or the implication that some scientists fudge the data or fudge the results to support the hockey stick or to support this concept of man-caused global warming, what impact that's had on greenhouse gas emissions and the whole area of global warming. I'm in that area, and it's had a very big impact. Whenever the leaders are accused of doctoring the data, it really hurts the cause. And I don't see why we don't have the same thing going on in quantum field theory. It seems like it's going to happen because it just isn't right.
Well, probably not in my lifetime.
Yeah.
I mean, I'm quite amazed at how utterly resistant anyone who's actually in the field I talk to is to asking questions about renormalization.
Yeah.
Their view is, you know, this 11 significant figures of agreement for quantum electrodynamics can't be a coincidence. There must be something in it. I don't doubt there's something in it, but it doesn't mean that you should give up, you know, finding the deeper explanation.
I just want to ask you that 11, and this is for clarity here, that 11 decimal places of correlation, which is the QED, quantum electrodynamics.
Yes.
Is that after subtracting the infinities?
Yes.
Okay.
Yes.
Okay. So that's sort of important because when you cheat to get the right answer, you're still cheating. I'm sorry to interrupt you, but I just wanted to get clear on that. Okay.
No, interrupt away. It is obviously cheating.
Yeah.
But I think the point is that if they got say 1.5 for the enormous magnetic moment, the electron, and then say, oh, that can't be right. Let's change it to 1.00 whatever it was, which was the experimental result. then people would immediately raise a flag and said, well, you're obviously cheating. But they don't cheat there. They cheat much further upstream
Yeah.
or downstream, upstream.
Yeah. Upstream.
But my concern is they're not, any assumptions or any sort of extra baggage being added to it should be done right at the start. You shouldn't be allowed to sort of start on the quantum field theory path and then say, oh, well, we sort of seem to have it right, but this infinity is very inconvenient. Let's just sort of change that. That is not science. That is just stupidity.
Yeah. And once again, it seems as if a lot of the literature on modern science, physics, cosmology, there's always a couple pages or maybe a chapter on the scientific method and about how science is always progressing. They never really have a right theory. They only have better, they're in the search for a better theory, a more complete theory. And all that seems to be true as an aspiration. But with string theory and with this quantum field theory and the renormalization, it seems as if some people, and maybe we have to say the thought leaders, have given up questioning their own theories, and that bothers me. When
I
it
I
just bothers
think
me.
I would certainly say that the kind of hard-headedness that the generation who were active around immediately before and immediately after World War II. I'm thinking of the original quantum mechanics and then the likes of Feynman and so on. The hard-headedness of them seems to have gone away over the years. And although that may have made them obnoxious human beings sometimes, it was fruitful in terms of science. We seem to have moved into an age where they're hippies.
Yeah.
There isn't actually any very clear right and wrong. You can say anything and everyone will agree with you, but that's not interesting. It's much more interesting if someone disagrees and explains why, because then you can gain understanding that way. Um, uh, Anything goes. I mean, string theory, it seems anything's possible. Um, but as far as I'm concerned, if anything's possible, then it's not a scientific theory.
Yeah, yeah. I read recently in Scientific American. I think there's been a couple good articles in that magazine recently about the multiverse and about the inflationary Big Bang. And one of them, I forget which article, I think it was Paul Steinhardt, who said something like, "A theory that explains everything explains nothing," which is a good way to put it for superstring theory. I want to emphasize something here, that even though you are a radical in actually questioning renormalization, you have very good company on the front page of your website, or at least the article on your website. You have two quotes, one from Paul Dirac and one from Richard Feynman, both of whom seriously question renormalization. In fact, Richard Feynman calls it a dippy process, which sounds like fudging to me, and he also uses the word hocus pocus, and then Dirac calls it a stopgap procedure. So it's important for the listener to understand that we're not talking about some far out idea here. We're talking about questioning whether quantum field theory with renormalization is the final complete theory of physical reality, or whether it can be, since it includes such a gigantic fudge factor. Uh, now, now let's just talk briefly about this famous God particle, the Higgs particle. Is that something you've been following as well?
Oh, well, how can one not?
Yeah.
I even took out the bet on an online gambling site and made myself about $25 by betting that they wouldn't find the Higgs in 2011. I'm not sure I would do the same thing for 2012, though.
Well,
Uh,
it's yeah. Well, what is? Let's describe for a second. I mean, we've talked about on this show. I've talked a little bit about the Higgs particle, believe it or not, because it's got such a catchy name. Uh,
Mm.
the God particle. But is there a relationship between the search for the Higgs particle and the quantum field theory problems or renormalization? Is there a relationship between the two?
Yes, there is, because quantum electrodynamics, which just describes fermions, which mostly means electrons, I mean, and photons, which is light, is extended to deal with the weak interaction. And the electroweak theory to which the Higgs is regarded as the solution is essentially a sort of slightly more elaborate version of quantum electrodynamics. So yes, they're very much the same thing, and you still have to do renormalization with the Higgs particle. In fact, the reason why, um, or let me just explain a little bit more. The photon has zero rest mass, as I probably mentioned earlier, and as I'm sure a lot of listeners will appreciate. But the particles that mediate the weak interactions do not. They're quite heavy. And if you have heavy radiation type particles, like for the weak interaction or even a massive photon, the theory is not renormalizable. And the Higgs boson was created as a way of getting around the non-renormalizability of the theory. So, I mean, the things are very, very closely connected.
Yeah, and once again, we have a problem here because physicists and cosmologists talk in such a technical language, and they're so far down the path of trying to authenticate their theories that to explain this to the common person on the street usually meets with uh, glazed eyes, and that's why I started off by talking about a model and reality. Now, and so what we're talking about here is we're talking about a theory or a model of reality that modern scientists are trying to develop to describe what reality is. And what we're learning from the renormalization is that scientists are making things up. They're cheating. They're fudging the data or the mathematics to make their favorite theory conform to how they want reality to be. The Higgs particle, which is this uh, theoretical particle that's supposed to supply mass to the other particles, is a missing piece of the puzzle that, in my mind, it's a piece that they need to fill in the blanks, right, or to fill in some missing theoretical or mathematical gap. Is
Yeah, no, that's
right?
absolutely right.
Yeah.
It's a. I mean, I really, really hope that the signals of the Higgs are turn out to be false, because if they turn out to be correct, then it will give a new lease of life to what is essentially a flawed theory. But
Right.
I mean, the framework such as they have it, with the renormalization and everything, does require it to be there. I don't see why it needs to be there at all. And maybe there is some deep reason, but whatever reason they have, it's not very deep at the moment. It's based on a flawed framework.
Right. Right. And I think that this is important, and one down to earth way this is important is because the Large Hadron Collider, this super collider particle accelerator in Switzerland, um, cost about $6 billion. It's about there's thousands of scientists working there. I think the U.S. put in something like $300 to $500 million, and 25 other countries helped fund it. This device is looking for all of these missing pieces to the puzzle. It's intended to, what I think is to propagate the wrong theory, right? I mean,
Well, Yeah, but it's an experiment.
Right.
That's the whole point. And I can assure you the quality of people working on these experiments is very, very high. I mean, if there is no Higgs there, they will not budget, and you can't budget. The more people are involved in the collaboration, the harder it is to cheat, because there's
Yep.
always going to be someone who's going to put their hand up and say, no, you can't do that.
Yep.
Um,
That's true.
so I have no question about their integrity and so on. But the danger is if they're using flawed theories to decide what they should be researching, then they're wasting a lot of time, energy, and money.
Yeah.
Um, Someone needs to come up with something a bit more um, solid on the theoretical front.
Yeah.
Um, but to give them, but you see, the problem is it's the other way around. Is someone like me who works from first principles and tries to observe mathematical proprietaries like not doing renormalization, uh, does not have um, a suggestion as to what they should be looking for. Whereas with renormalized, um, Yang-Mills theories, which is what they're using, spontaneously broken symmetries, they do. They say, well, there must be a Higgs particle there. It's very boring for an experimenter not to be told what they should be looking for, and it's very hard to fill in a grant proposal on the basis of a wing and a prayer. It's much easier to do it if there's a very specific thing you're looking for.
Yeah, and I think that that's a better way to express my point, perhaps, because it goes back to this idea that if the thought leaders, if the most honored scientists in the field are following this theoretical pathway, then it's hard to dislodge them and get the funding, the money, the attention to try and experiment with some other theory, right? Right. That.
Uh, that's true, but I mean, the big problem with me is I wouldn't be able to tell them what to look for,
Yeah.
because it's still very preliminary, and I haven't actually been in a full-time researcher
Right.
for decades.
Right.
Um, but I would hope that we would have, assuming they find all the particles that theoreticians predict, and don't forget, theoreticians have had a pretty good run for their money. I mean, the W boson, the Z boson in the 80s, those were all discovered, and they were where people thought they would be in terms of mass and energy, etc.
Right.
Um, and in a way, it's been a victim of its own success.
And that is the big problem. I mean, one thing from Leon Letterman's book, The God Particle, that's always stayed with me is that he said something on there about the goal of science or physics is to have a theory that'll fit on a T-shirt,
Yeah.
and that's a nice goal, and that to me means it could be understood. But when these theories get so far afield into the math, and of course string theory is a whole nother world, it's a little hard to imagine the common person ever understanding it or ever wanting to understand it.
Well, they don't even understand it themselves. They don't even know what string theory actually is.
Yeah.
I mean, the best way it was described was by Tuft, the Dutch physicist, Nobel laureate, who just said it's a hunch. It's not a
Right.
theory; it's just
Right.
a hunch.
Right.
I mean, I cannot claim any deep knowledge of string theory other than the anecdotes. So
Yeah.
I never really got into it. But to me, it's just another example of the lack of hard-headedness. There's this saying, this quality of being discriminating seems to have just missed, a couple of generations of physicists. Ed Whitman says that string theory is cool, so suddenly thousands of others are studying it. I mean, don't they ever think for themselves?
Yeah, and as you point out in your article, Brian Greene is a real good salesman. he has his books are good except for the last one, which I thought was hard to read. But he came out with very nice looking, well written books. You know, The Elegant Universe and The Fabric of the Cosmos, um, talking about how great and cool string theory is. And it sounds like, wow, this is really a neat thing to do until you get into the details. That's what was so refreshing about Peter Watt's book and and Lee Smolin's book is really basically saying where they said there's no experiment that could ever prove it right. Um,
Or prove it right or prove it wrong. I mean,
right.
that's the problem. Is if you can't prove it wrong, it's not a scientific theory.
Yeah.
You know, but no, I mean, actually, I have to say, my interaction with Brian Greene which was a long time ago in Oxford, was good. I thought he was this clever guy who was, doing it for the right reasons.
Yeah.
But obviously, I wouldn't agree with his view on string theory because it's just a huge staircase to nowhere.
Well, my first of all, I think that Brian Greene is obviously a very talented, intelligent
Yeah.
person, and he writes well. My problem is the forthrightness issue. Is who out there says here are theories and here's what we don't know. There's so few people, there's so few books you could read other than um, folks who are in more of the New Age spiritual genre, who are trying to who expose what they don't know, and we're not saying to admit that you're wrong, but what I'm saying is tell us where the gaps are, so at least be honest about it. That's my problem with a lot of these books out.
Well, yes. I mean, the thing is, establishing the truth is what you might call a negative thing. You're mostly looking for things to fail rather than for things to work.
Right.
And testing a theory like Newtonian theory doesn't quite work when things are traveling very fast. So you're saying Newton was wrong. Um, this quote from Planck you had about physics progressing from funeral to funeral. Well, that's the way I look on it. Is it's essentially um, each new generation of theory is a entity in itself, and
Right.
effectively what it does is it makes the previous version irrelevant. It doesn't. It builds on it only in the sense that it gives it clues as to where to start. But essentially, it's a place. It's more like it is more like people um, living and dying. It's like you have Newton, and then he dies, and then you have, I don't know who was immediately after Newton, but you eventually get to Einstein, and then when Einstein dies, someone needs to come up with something better than his theory, or he carries on living for a few more generations if what he's done is really, really great.
Right.
But it's a process of replacing, not enhancing the previous theory. I mean, it's enhancing in a sense, but mostly it's about a surgical removal of the previous theory and supplanting it with something else.
Yeah, I thought that your point that you made earlier about science still has people is really a insightful point, sort of an obvious
Well,
point, but it's sort of like it maybe it's hard not to be subjective.
well,
Uh,
that's right. But I mean, I would say that there are some very good physicists alive today, but they're not in particle physics.
right.
The people who are not in theory anyway. I think probably some of the best physicists are ones working at the Large Hadron Collider on
Yeah.
the experiments,
Yeah.
because these are the people who are trying to discriminate amongst, unbelievably, unimaginably huge numbers of collisions in these bubble chambers. What things are interesting and what aren't. They're the people who are asking the hard questions. What if this was a cosmic ray? What if it was this? They are applying what I call real physics, which is the kind of very intense critical analysis of the physical data in order to find a signal, to find some sort of process, something that could be related to physics.
Yeah.
Most of the theory people are just hot smokers. I mean, in obviously not necessarily literally, but in the sense of their attitudes. The attitudes are just, you know, let's think beautiful thoughts. But I mean, a lot of the thoughts aren't very beautiful. They're quite ugly, because you're striving and you try something, it doesn't work. It's not a good theory. You throw it out, you start again, and that's what makes the process interesting. And if people are just going to be very kind of uncritical, they're not going to do good science.
Yeah, and I think that this new revelation coming out of the neutrino faster-than light experiments is another good example, and that to me is on the good side, where ultimately the experiments have to support the theory.
Yeah.
And I don't know yet whether, I guess they're going to retest on whether indeed it was the cable that was that was loose, or whether the neutrino went faster than light, one of the two. Um, but that's a good example of sort of taking a step back and redoing it, and that's where you got to give the scientists credit. I mean, I'm not. My problem is when you have a theory that's obviously wrong or incomplete, but to pretend as if it's the final word. Uh,
Well, right. Now, if they'd said to me in 1984, oh, so you think you can do better than renormalized vibration do? Let's see you try.
right,
Here's 3 years of money, or even 1 year of money. That's not what happened. You
right.
know, they didn't even want to talk to me. As far as I'm concerned, they were concerned I was no longer one of them. I was not part of their club, um, and they didn't want anything more to do with me.
Yeah. Well.
Uh, where the difference with the faster than light neutrinos is, they've got 1,000 people, well, tens of thousands of people saying, this is such a well-tested theory, but you've got to have been doing something wrong. But on the other hand, they keep the little window open. If you really have got neutrinos going past the speed of light, we are very interested. And then if it could be tracked to a loose cable, then fine. But people are keeping an open mind in the way that they were not with me in 1984, possibly because there was only one of me,
Right.
where there's a whole team of them in Gran Sasso laboratory in Italy.
Yeah.
You know, um,
Yeah. Well, as I said, I personally have faith that the truth remains standing, and unfortunately, sometimes it takes a long time. But gotta keep. It does not hurt to be critical and to put people to task when either the data doesn't support the theory or the theory is contrived. So, Doctor, I will let you go. It's been a pleasure talking to you once again, and thank you for the extra time here. But I will send you a link to the show. It will be out on March 12th,
okay,
I believe, and
okay,
and hopefully we'll follow up a little bit here or there to see what happens. But good luck to you, and I really appreciate your time.
okay. Nice talking to you.
Okay, take care of
Yeah,
yourself.
yeah, yeah. Take care.
Bye bye. I think that from the side of thinking about this positively or optimistically, the whole enterprise of science is based upon looking for the truth that remains standing, or the theory that will withstand all criticism. And so what we've said on this show with Dr. Oakley here is that the current quantum field theory has a fundamental, and some would say fatal, flaw in that it requires a renormalization or a fudging of the mathematics in order to remove infinite quantities. And however fancy that sounds, at the end of the day, there is some cheating, some doctoring of the mathematics going on, and therefore it looks as if this is not the right theory, and that science's quest for that ultimate theory of reality is not yet over. Now, Doctor, I'd like to thank you for your time today. It's been very informative. We've dealt with a difficult topic, but I wanted the listeners to understand that this is something we should all be paying attention to, because it shows that, as I said, the job of science is not yet over. I would encourage folks to look up Dr. Oakley on his website, and take a look at his article, The Search for a Quantum Field Theory, and I'll give you the website. It looks like it's www.cgoakley, Oakley, and you'll see that his thinking is, even though it's radical, it's also very tight, and his support is actually by some of the leaders in the scientific community, or at least the historic scientific community. Doctor, I'd like to thank you for your time. It's been, as I said, very educational. And this is Philip Meriton. My website is www.heavenattheendofscience.com, where you can learn more about my own views on these and many other topics in the same area. Thanks for listening, and we'll see you next week.
Thank you very much.
Thank you.